Welcome to the lair of the Batty Boffin.
Hi there, Batty fans. Time for a bit of juicy maths with the Batty Boffin. Now, when I was wandering around in my world of maths, as I do occasionally, I came across this rather nice little neat thing. Makes a nice pattern. 1 cubed equals 1 squared. Well, that's no great shakes, we kind of knew that. But what happens if you add 2s and 3s to it? 1 cubed plus 2 cubed, that's 1 plus 8, which is 9, is equal to 1 plus 2 squared, which it does. How very nice. Works with 3 as well. 1 plus 8 plus 27, I hope you know. Add that lot up, it comes to 36, which is 1 plus 2 plus 3 squared. And I saw that and I thought, oh yeah, that's quite nice, isn't it, that? I wonder if the pattern continues, because, I mean, sometimes you get things like this that are just random coincidences, like, for example, 1 plus 2 plus 3 is equal to 1 times 2 times 3. Very nice and neat. But it doesn't work for 4 and it doesn't work for 5. It just works for that one. So I wondered on this, I thought, does that work for others? So I'd like you to test it out, please. Could you write out the 4th line of this and the 5th line and just check that it works? See you in a minute. Okay, hopefully you verified that it is in fact true for the 4th and the 5th terms. So seeing that, we kind of think, it's probably not just coincidence that it works for all of them. This is thinking that it might be a general thing that works for all terms. And in fact, it does. And we're going to prove that using something called proof by induction. So the way we're going to use that is by using some of the n notation. So for this particular thing here, this is term 1. That's the first thing, the first term in the series. That's term 2, the second in the sequence. That one is T3, and we are going to write out Tn. So Tn is equal to 1 cubed plus 2 cubed plus ... plus n minus 1 cubed plus n cubed. So that would be the nth term. Hope you're familiar with that kind of format. And what we're saying is we want to show that that is equal to 1 plus 2 plus ... plus n minus 1 plus n, whole thing squared. That's what we're hoping to show. Okay, so that's the nth term on the left-hand side, the nth term on the right-hand side. Now, I don't know about you, but kind of, adding all that lot up and seeing that it's equal to that would actually be quite difficult because we don't actually know what n is, and we do not want to have to do it for every case. And even if we did do it for every case, that wouldn't actually help, because just showing that it is true for the first 5 cases doesn't mean it's true for the 6th. We suspect it probably is, but we haven't proved it. Even if we did it for the first 100 cases, that wouldn't prove that it was worked for the number 101. And in fact, you could go as many times as you like, just demonstrating that it worked, but that would not prove that it worked for all of them. So, proof by induction is a very clever thing. What we do is we show that it definitely works for one of them, and it absolutely does. 1 cubed is the same as 1 squared, it just is the same. And then we use some algebra to prove that if it's true for this one, then it therefore has to be true for the next one. So that means that if we've shown it works for number 1, the maths will prove that therefore it works for number 2, therefore it works for number 3, therefore it works for number 4, blah, 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 for as many as you like. So we only actually have to demonstrate one, and we use the algebra to go on to the next one. So how are we going to do that? Well, what we're going to do is look at the left-hand side and the right-hand side for 2 consecutive terms. So for example, between term 2 and term 3, we're going to look at what we did to the left-hand side, and then we're going to look at what we did to the right-hand side. And if what we did to the left-hand side is the same as what we did to the right-hand side, then we know that if term 2 is true, term 3 must be true, because if you do the same thing to the left and the same thing to the right, then this equation is still equal. So I will just say that again. What we're going to do is we're going to look at the left-hand side of a term and the next term. We're going to look at the right-hand side of a term and the next term, and we're going to see what we did. And once we've got that difference, we're going to try to show that the difference on the left-hand side is the same as the difference on the right-hand side. And so if we've done the same thing to both sides, then the two sides that were equal in the first one must also be equal in the second one. Okay, that's called proof by induction. And here we go. Right, in order to look at what we've done to both sides, I've written out two adjacent terms. Here's my term n, okay, 1 cubed plus 2 cubed plus, I put two terms at the beginning and two terms at the end. Well, actually I put three terms at the end here, haven't I? N minus 2 cubed, n minus 1 cubed and n cubed. So that's my left hand side. And here's my right hand side, 1 plus 2 plus n minus 2 plus n minus 1 plus n and the whole thing squared. So that's my term n. I've also put in the term before it, which is term n minus 1, written in black. So here we've got exactly the same thing, only instead of finishing at n, we finish at n minus 1. And again here, instead of finishing at n, we finish at n minus 1. And what we're going to do is look at what we've added to the left-hand side to turn the black into the blue, and what we've added to the right-hand side to turn the black into the blue. And hopefully we will show that those are the same thing, but we'll work on that. So, for starters off, D left and D right. Now D left is pretty easy, D right's a little more tricky. So, could you have a look at these two equations? Please pause the video, write down what the difference is on the left hand side. Basically, it's what do you do to turn that into that, what do you add to turn the black one into the blue one. This one's a little more tricky, okay, we'll work on that together. Okay, pause the video. Right, you should have for the left hand side, pretty easy, the difference is n cubed. That's all we did. For the left hand side it's exactly the same, we just added n cubed. Now for the right hand side it's a bit more tricky because we've got this squared brackets here. Now we could multiply it out like a huge lot of quadratic brackets, but we're not going to because for start we don't know how many there are in there, it would take a very long time. What we're going to do is look at the things and spot the things that are the same and the things that are different. So for example, here's a great big bracket, okay, and I've written it out here as my great big bracket times by the great big bracket because it was squared, okay? And you'll notice that a lot of it is the same in here. So when we multiply these out, we'll start off, we're going to get a 1 times a 1. But this bracket would also have a 1 times a 1. So that's no different, that's not changed. We're also going to have a 1 times a 2. But so would that, so that's no different. We're going to have a 1 times a load of things. A 1 times the n minus 2, yeah, got that. A 1 times the n minus 1, yep, got that. Until we get to the 1 times the n. That's new. So on the right hand side we have an extra 1 times n. From that 1 times the n. All the others are the same as the black bracket, so we don't need to count those. Same with the 2. We've got a 2 times a 1, already got it. 2 times a 2, already got it. Everything until we do the 2 times the n. That's new. Plus 2. I'm going to write that as 2n. I'm going to write that as 1n because I can't be bothered to write all the times in. So we've got a 1n and a 2n. And then we're going to have a 3n and a 4n and all of those there. Plus dot 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 dot. We're going to have the n minus 2 times the n minus 1 times the n, all of these here. So n minus 2 n's plus n minus 1 n's. And then of course we're going to have the n times the n as well. And more. Because as well as this n times the n, we're also going to have the n times the 1. Because we didn't have the n in the first brackets. So we're going to have another n times the 1. And the n times the 2. And the n times the 3 and the n times the 4 and everything else, plus dot dot dot, plus, oh I'm going to read it in, n minus 2 n's plus n minus 1 n's. I don't need brackets there, do I? Just got it in there. So we got to the n times the n minus 1. The n times the n, of course, we've already done. So that is the difference between the two left-hand sides, and all this is the difference between the two right-hand sides. Which I have to confess doesn't actually much look like it's going to be the same as that. But wait, it will. I'm going to pause the video again because I've got to wipe down all of this, and what we're going to do is simplify this long green thing. Okay? So, pause the video, quick cup of coffee, custard cream while I wipe down the board. See you in a minute. Right, that's a bit clearer. I've just written out those two differences again. The difference on the left-hand side was n cubed, and the difference on the right-hand side was this great big long thing here, which we've got to try to show is the same as n cubed, and I realise it doesn't look very hopeful at the moment. But we can simplify this a lot. First thing we can do is note that every term has got an n in it. So, first thing for you to do is pause the video and factorise that by taking n outside the brackets. Okay, here we go. Okay, there it is with n outside the brackets. Looking a little bit clearer, isn't it? Now we can note some rather nice things. It's all beautifully symmetrical with this n in the middle there. So there's our n in the middle. And the things on the left-hand side and the things on the right-hand side match. And they match up rather nicely. 1 can match with n minus 1. Another colour. 2 can match with n minus 2. And there'll be a 3 that matches with the n minus 3, and all of them right up into the middle where that n minus 1 matches with that 1. And you'll see when we add them, because all these terms are added, you've got a 1 plus an n minus 1, which makes n. You've got a 2 plus an n minus 2, which makes n. You've got a 3 plus an n minus 3, blah, 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 blah. n minus 2 plus a 1, so n minus 1 plus a 1, which makes n. So in fact, all of these paired up terms equal n. Question is, how many of these paired up terms have we got? Well, that's the first one, that's the second one, all the way along. Everything on the left-hand side pairs up with something on the right-hand side. So we have how many paired up terms? n minus 1. So, see if you can write that in maths. This one's a bit tricky, so don't worry if you can't do it. Have a go at that. Okay, if you got this, well done. How many n's have we got? We have got 1, 2, 3, blah, 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 n minus 1 of them. We've got n minus 1 n's. Plus, of course, we've got that one in the middle there. Okay, so these added up with these all fold over onto here and make n minus 1 n's. Plus another n that we've got. Right, that's now quite simple on there. You should be able to do that. Multiply out that inner set of brackets, simplify, gather together like terms, divide by the square root of your phone number and come out with the answer. Okay, pause the video and do that now, please. Okay, here's what it should look like. N multiplied by, multiplying at the inside brackets, we've got an n times an n, which is an n squared. Take away a 1 times an n, which is a minus an n, plus that n that we had with the red circle round. Obviously those two bits cancel out and we're left with n times n cubed, n times n squared, which is n cubed. Ta-da! Left hand side equals the right hand side. That means that what we did on the left hand side, the change from the one term to the next, is exactly the same thing as what we were doing on the right hand side, the change from each term to the next. So if term 1 was true, which it was, and in order to get to term 2 we did the same thing to the left as to the right, and we have proved that you have, for whatever number n is, it will always be the same. So if it was true for term 1 and you add the same thing to the left and the right, then it must be true for term 2. And if it's true for term 2, then by doing the same thing to the left and to the right, it must be true for term 3, and so on to infinity. We have therefore proved it is true. Q-E-D. See you next time, Batty fans.